Hi, welcome to Chem 2. Yeah. Hey, last year for Chem 1 we talked about a lot of things, and one of the reasons many of you took Chem 2 this year instead of physics is because you didn't want to forget all the things that you learned last year in Chem 1. And that's a good thing. You did the right thing in doing that. But you're going to find that it may not always be that easy to remember, so I will be helping you through this, and hopefully this will be one of those things that you'll, oh yeah, now I remember, I kind of don't remember, but now it's kind of hit me. So that's the goal. It's not only to teach you brand new stuff, but to reinforce what you've already learned and get it more to the front of your brain than in some recluse in the back part of your brain. This is a good example of this. We're going to deal with dissolving reactions. Now, we did do some dissolving talks last year. I sent a bunch of stuff out for that. We're going to really reinforce it now. We also talked about reactions last year. And we did talk about that before the pandemic hit. So this should be, hopefully, becomes somewhat familiar to you, especially after we talk about it. But the one thing you have to have take place in order for a reaction to occur is a collision. A reaction occurs when two substances collide, causing bonds to break and forming new bonds. So it's like, and then all these particles come flying off if it's hitting strong enough. Dissolving is a type of that reaction. Because if you think about when you dissolve stuff, you got to pour, usually it's some kind of solid into the water, or the water into some kind of something. Think about Kool-Aid. You think about Kool-Aid. When you make Kool-Aid, or if you make Kool-Aid, Kool-Aid was a thing when I was a kid. Hopefully we've grown from that, but I'm hearing not necessarily. But when you pour water into a container with a thing of Kool-Aid on the bottom, the instant the water hits, because of the force at which the water is coming down on top of it, is a collision. But the coolest thing about making Kool-Aid is actually starting with the water and the Kool-Aid, and watching the little particles of Kool-Aid kind of drift through and start to disappear, but the color of the water changes. And that's because there's still a lot of motion taking place. All particles move, unless it's absolute zero, which is like 454 degrees below 0 Fahrenheit. Nothing's moving, and nobody really cares because everybody's dead. But the hotter it is, the faster things move. So when you're making Kool-Aid, the water particles are constantly moving around. Now they're all bonded to each other, so it's kind of like a bunch of slime going around. But when a particle hits it, it is easily broken apart, and that's when the reaction takes place. Dissolving is a type of reaction, but it is not completely a reaction. It fits the definition, but the new bonds formed are not internal, they are external. And what I mean by that is that when a reaction takes place, a true reaction, the bonds that hold the atoms together break apart, and they form new bonds either with each other or with other particles or whatever. These will create bonds, but water stays water and Kool-Aid stays Kool-Aid. But when water attaches itself to Kool-Aid, that's when we get to drink it and it tastes better that way. Otherwise, you may as well just open up the packet, throw in some sugar from a measure, stir it up, and just down it that way. But that's dry, that is not nearly as tasty if you use a liquid form of it, so we dissolve it in water. Now, the internal bonds are what's taking place inside the molecule. There are two types of bonds. We talked about this before the pandemic hit as well. Ionic and covalent. Also known as intramolecular bonds. Covalent bonds are known as intramolecular bonds. The external bonds are hydrogen bonds, dipole bond, and van der Waals forces. And they're called intermolecular bonds. Dissolving reactions involve the latter bonds, the intramolecular bonds, not the former bonds, but the intramolecular bonds. Okay? So we're focusing on what kind of bonding is going to take place when this dissolving occurs. Now, When dissolving takes place, two categories of substances are present in the eventual solutions. The solvent, which is doing the dissolving, and the solute, which is being dissolved. In the case of a combination of water and a solid, like water and Kool-Aid and sugar, the water is usually the solvent because it tends to be the more abundant quantity of the two. So the greater the amount of material, that is going to be considered the medium of dissolving. Everything's going to be blended into that. The solvent can be the same phase as the solute, but it must be the more abundant quantity of the two. Okay, so like if you're, I don't know, let's say you're mixing lemonade with some beverage, shall we say? They're both liquids, but since you probably have more lemonade than whatever liquid you're adding to it, whatever that is, that lemonade is going to be your solvent, and that whatever it is going to be your solute. Just for the purpose of giving the name for the two substances compared to the mixtures of different phases. The process is the same, no matter what you call the solute, whatever you call the solvent. There's bonding taking place externally between these two substances. But because we have more of one, we call it the solvent, and less of the other, we call it the solute. Let's use the idea of sodium chloride dissolving water. Water is the solvent and not flowing independently in the water. It is actually bonded to the other water molecule before the sodium chloride comes into play. So let's find that, shall we? Here is water bonded to each other. Water does not move independently. Gases do that. When gases are around, which they are constantly, thank goodness, or we'd be dead right now, they are independent, one atom at or one molecule at a time, bounding into another molecule somewhere and constantly moving around, and they don't react if they are what we call ideal gases. Nitrogen, ideal gas. Oxygen, ideal gas. When they collide, they don't stick together. They don't create new compounds. They bounce off each other. Water is not like that. Water is what we call a polar molecule. It has a positive side and a negative side. The negative side is where the oxygen is. The positive side is where the hydrogen is. And the reason for that is something called electronegativity. You will see that the water has a positive side, represented by a lowercase delta. Okay, so let's take a look at that, what a lowercase delta looks like. You may not have seen it very well on this little chart of mine here. And that's not it, that's not it, that's not it, that's not it. There it is. That is a lowercase delta right there. We saw that on this thing right here. These are lowercase deltas. Now the reason why they're lowercase deltas, in other words, in English, terms of English, we have capital letters and lowercase letters. Capital delta is a triangle. When we talk about exothermic and endothermic reactions, we talk about something called delta H. They're the triangles. That's capital delta. Lowercase delta implies that it's not very strong. So these aren't truly positive and negative charges like sodium chloride has. Sodium has a true positive charge, and chlorine has a true negative charge when it reacts. Water doesn't have a true positive and a true negative. What it has is a separation where electrons are found more in one area than in the other area. And the one that has the more electrons around it is the oxygen, and the less electrons around it is the hydrogen. So we have a slightly positive charge here and a slightly negative charge here. They aren't true ions, they just pretend to be. And they're all linked together. In fact, it doesn't show it here, but every water molecule has 6 other water molecules bonded to it in this fashion. This is just a really good representation of 4 of the 6 that bond around it. There's going to be 2 behind the board that you can't see. Okay? That kind of bond where the hydrogen is positive is called a hydrogen bond, because the hydrogen bond is the strongest of those external bonds, what we call intermolecular bonds. Okay? They're polar bonds, better known as hydrogen bonds, break apart and become available to bond to another oppositely charged particle. So when something collides with the water, all those bonds we saw there, because they're kind of tentative in their own way, not like ions, which are really strong, they break apart. Sodium chloride, however, is not a molecule. We find sodium chloride in clumps. Clumps. It is ionic. In fact, you can find it here.